It is my great pleasure to introduce our next speaker, Iulian from the University of Graz, from the University of Vienna, sorry. This is the second time that Iulian is giving a talk at a conference in Graz that I'm co-organizing. My groups, yeah. So yeah, as always, it's a great pleasure. Iulian will talk about the meaning of reconstructed quantum mechanics. So yeah, I'm very much looking forward to this. The floor is yours.
Thanks very much for organizing this nice conference. I'm happy to be back to Graz, one of my favorite cities in Austria. So let me start by with a little, advertisement for the a big conference on the Vienna Circle that we organize the Institute of Vienna Circle in September. For 3 days, so it's going to be a conference at least as big as this one, right? With plenty of good people, good historians, and philosophers of science. So mark your calendars if you're interested. Also note that there is a little button. If you check out, the website, there is a little button over there that says fellowships, right? So if you're interested in coming to Vienna and do some philosophy of physics, we have a research group together with the Institute for Quantum Optics and Quantum Information, and we organize, meetings and having fun doing philosophy of physics. So in particular, just to give you a sample of what we are interested in, questions like this: can quantum mechanics be rationally reconstructed? And by that, we mean something else than it is usually meant by reconstructions of quantum mechanics, right? Rational reconstruction in philosophy, in the history of philosophy, and in particular in the history of logical empiricism, and more particularly Vienna Circle, has specific meaning, right? So a rational reconstruction is a particular kind of formal language. So the question about whether quantum mechanics can be rationally reconstructed comes down to the question of whether quantum mechanics can be formalized as a Carnapian language. What does that mean? Well, that's a language that distinguishes clearly between semantics and syntax and defines a notion of consequence that helps one model the inferences in a particular, in this case, in quantum mechanics. So something very useful to do. There are, however, very serious obstacles. So again, I'm gonna just show you a sample of such obstacles. Suppose one reconstructs quantum mechanics as a Carnapian language, as I briefly said, one can do. It is an experimental fact that quantum mechanics makes any empirical claims at all, in the sense that there is inductive evidence that that is the case. However, if quantum mechanics is reconstructed as a Carnapian language, one cannot know that it makes empirical claims unless one can prove the consistency of quantum mechanics. Due to Gödel's second incompleteness theorem, that cannot be proved, at least in an informative way. So one cannot know that quantum mechanics makes any empirical claims. Therefore, quantum mechanics cannot be reconstructed as a Carnapian language. Okay? So obstacles like this are, really interesting. We take them seriously, and we hope to, we hope to develop a project that will attract a lot of philosophers, a lot of physicists, a lot of historians of the Vienna Circle, people interested in Carnapian studies, to work on stuff like that. So if you're interested, whether you are just finishing your PhD dissertation or you're a world-class famous scholar, do send an application. We have generous financial support, so come to Vienna. Okay.
Is this only for young people, or?
It's for everybody.
Okay.
Everybody interested in stuff like this.
I'm interested in
I should say. Yeah. Send an application and, hope for the better then. All right. This is not what I'm going to talk about today, though. The goal of my talk today is to raise a problem, another problem, or as Chris put it over lunch, to punch a hole in a view that Richard Healy developed recently, starting with mainly his book on quantum mechanics, his 2017 book, The Quantum Revolution in Philosophy, where he develops a view that he calls pragmatist inferentialism. So let me start with a quotation from one of my favorite philosophers of physics in Vienna, Markus Müller. This expresses a common sentiment, though. The new approach to quantum theory, that is the reconstructivist approach, from the outside provides a very illuminating perspective on quantum theory itself. It allows us to understand which features are uniquely quantum and which others are just general properties of probabilistic theories. Very nice, and I think quite true. Here is a quotation from a talk that Healy gave at ECOC quite recently, several months ago. He says, "We can understand quantum theory better if we stop asking how it represents the world and ask instead how we are able to use it so successfully in predicting, explaining, and controlling the world." Again, a common sentiment, right? Now, looks like if we put together these two nice things, reconstruction and inferentialism, we get double epistemic benefit, right? We understand better quantum theory because we approach it from the outside, as in the reconstruction program, and we understand better quantum theory if we stop asking how it represents the physical world and focus on other things. My point today is that this is too good to be true. So, and this is not, at least I'm not going to present it as a criticism of the reconstruction program, but as a criticism of inferentialism. So, I'm going to start by telling you more about inferentialism, since I cannot suppose that everyone is familiar with Healy's view. And to do that, I'm going to start with the $1 million question, which I guess is a question about the meaning of quantum mechanics. What else could it be, right? So, in the literature, answers to this question depend on whether ontology and semantics are conflated or not. If they are conflated, then the answer to this question takes the form of a psiontic interpretation of quantum mechanics. Right? So pointing to a physical ontology is supposed to give the meaning of the theory. If they're not conflated, and this would be the case of inferentialism, then the story about semantics can dispense with giving a story about ontology. However, the question is not as well posed as it could be. So a version of the question that I think is better posed is this: what is the relationship between the language of quantum mechanics and its meaning? And this is better because, of course, meaning is something that attaches to language, to linguistic expressions, rather than whole theories, right? And if you understand the question in this way, then the good thing about it is that there is a nice way to approach it. Explaining this relationship in the general case is a task of what is called metasemantics, what a philosopher at MIT, Robert Stolnaker, called foundational semantics. So in the case of quantum mechanics, we need to look into the metasemantics of quantum mechanics. Okay? Now let me tell you a couple of things about foundational semantics or metasemantics to see how this is relevant to answering the question about the meaning of quantum mechanics. Here's a quotation from Stolnaker, where he distinguishes between what he calls descriptive semantics and foundational semantics. What does descriptive semantics do? A descriptive semantics is a theory that says what a semantics is, what a semantics for a language is, without saying what it is about the practice of using that language, that explains why the semantics is the right one. In contrast, foundational semantics asks questions about what the facts are that give expressions their semantic values, their meanings, or more generally about what makes it the case the language spoken by a particular individual or community has a particular descriptive semantics. So, of course, Stalnaker was interested in natural languages, but nothing stops us from considering mathematical languages and even formal languages. Okay, so now the central question of the metasemantics of quantum mechanics is what makes it the case that expressions in the language of QM have meaning? Or as I prefer it to ask it, in virtue of what do expressions in that language have meaning? Now, the language of standard quantum mechanics is all familiar to everyone, so I won't spend any time on this. The question again is, in virtue of what do expressions in this language have meaning? As you can see, specifying the language typically comes together with specifying what corresponds to the mathematical objects in the structure, in this, structure denoted by the symbols over here, right? So you have a quantum state, you have dynamical variables, and so on and so forth. This leads us to the question about what answers to the question again being, in virtue of what do expressions in this language have meaning, what answers to this question are possible or available in the first place. So I'm here just mapping the metasemantic territory. One option is to take those correspondences seriously from a metasemantic point of view. And this is something that quite emphatically T modeling is known for doing. He says, the mathematical object, the structure that you've seen on the previous slide, must be supplemented with a physical ontology and semantic rules specifying how the physical ontology is represented by the wave function. Notice the inevitability of doing so that he emphasizes here, right? You must be doing this, otherwise, quantum mechanics has no meaning, right? You have to give a physical ontology. This is a prime example of conflating semantics and ontology. Now, if you ask in virtue of, just to make this more explicit, in virtue of what do expressions in the language of quantum mechanics have meaning, obviously it's semantic rules that do the metasemantic work. But notice that they do double work here, right? They do the work that Stalnaker called descriptive semantics, and also the work that he called foundational semantics, right? They say what the semantics is and also explain what makes it the case that the language of QM has that semantics. So in a sense, metasemantics is quite shallow here. It doesn't add anything to semantics, right? So you don't have to dig any deeper than the semantic rules, which you already have when you give the formalism. Other people think otherwise. As I mentioned, Healy defends a non-representationalist semantics. He says, all our concepts, including those of physics, derive their content from use in human communication. All right? So if you ask the same question, the answer is not going to be semantic rules or correspondence rules, those rules that attach to the mathematical formalism parts of physical reality. Semantic rules cannot explain, according to Healy's inferentialist, they cannot explain what makes it the case that the language of quantum mechanics has the semantics it does have. What exactly does that explanation for the inferentialist? What exactly explains what makes it the case, or in virtue of what do quantum mechanical expression have meaning? Before I say more about that, let me just characterize inferentialism in general terms. I like this term Neo-Bohrian. I think it characterizes nicely inferentialism, so I thank Mike for that. It is a Neo-Bohrian approach, and self-consciously so. So according to Healy, quantum mechanics has no Beebles of its own. There's no quantum dynamics. Schrödinger equation is used for updating credences in experimental propositions, what he calls magnitude claims that take the form this form over here, right? It's a certain magnitude in a certain interval. And structures like you've seen before are used as epistemic advisors, right? They're used for updating credences or adjusting degrees of belief in certain experimental propositions. In that sense, quantum mechanics is neither psi-ontic nor psi-epistemic. It is what Healy calls psi-prescriptive. And he takes both psi-ontic and psi-epistemic interpretations to be representational. That is, to adopt a representationalist metasemantics. A metasemantics that explains semantic facts by way of those correspondence or semantic rules. Not so with the prescriptive approach. So I think it's fair to say that inferentialism has a lot in common with both cubism and boobism. But this is a line of inquiry that still needs to be pursued. Of course, reading quantum mechanics of its ontology is not enough for rejecting representationalism or for endorsing inferentialism. One can very well be a quantum fictionalist. That is, you can separate semantics from ontology, deny that there is any ontology, but adopt a representationalist semantics. Right? So what your mathematical formalism then would represent is just fictions. All right? Another line of inquiry that needs to be further pursued. Right. What does do the metasemantic work according to inferentialism? What is it that explains, in virtue of what, quantum mechanical expressions have meaning? This is the role that Healy assigns to material inferences. And this is a kind of inferences that take you from a description of a certain experimental setup to the assignation of a certain quantum model, mathematical structure like that, and then via the application in proper context of the Born rule to a certain set of probabilities. There's a long history in the philosophy of 20th century that would need to be described in order to make full sense of material inferences. But in a nutshell, material inferences are not logical inferences. So they are not valid in the sense in which logical inferences are valid, right? Not valid in virtue of the form. Nevertheless, they are counterfactually robust. That is, if you change a little bit your experimental setup, then you would get different probabilities because you would most likely assign a different quantum model. Now the argument for the irreducibility to logical inferences is quite, will take us astray. So I don't spend any time on, and it's not important actually for my purposes today. The way to read this material inferences to make sense of the counterfactual nature is as subjunctive conditionals, right? If the experimental setup were such and such, then probabilities would be such and such. This would make it immediately clear that these are not logical inferences, but if you're curious about this, let me know and I can explain this in the Q&A. So for example, take the traditional cat-hating scenario with the cat in the box, right, with a flask of poison, radioactive atom, right? This is the description of the experimental setup. Based on this, you assign a certain state, you let it evolve, and then in the end you get probabilities for each of these two options, right? The 1/2 probabilities. Atom hasn't decayed, the flask of poison isn't shattered, Findus is alive, and the other possibility as well has the same probability. The important point for the inferentialist here is that all expressions in these inferences derive their meaning from their use in such inferences. So there is no semantic rules that provides the meaning for these terms. And this is This is so not only for the quantum mechanical terms in the inference, but for terms like names, Findus, box, flask of poison, atom, so on and so forth. All of them, remember Healy's quotation, right? The quotation from Healy. All of these concepts derive their content from their being used in inferences. Of course, the network of material inferences is huge, right? So there's a lot of inferences that contribute to the meaning of these terms. Right, so here are some of the characters. This is Stolnecker, right? Still active at MIT, I take it, although he's 80-something. Tim Maudlin and Healy and Findus. Right, so now, having said all that about inferentialism, my interest today is in answering or approaching this question about the metasemantics of reconstructed quantum mechanics. Right? So in virtue of what do expressions in the language of reconstructed quantum mechanics have meaning? And so we have the same two options. There might be more than these two options, but I'm just going to focus on inferentialism, in particular on whether the reconstructivists could adopt an inferentialist metasemantics for quantum mechanics. But first, I'm going to talk about whether it is possible for the reconstructivists to adopt instead representationalism. One option, if you are drawn to that possibility as a reconstructivist, right, would be to just take up the semantic rules of a psiontic interpretation. Any psiontic interpretation that fits the bill. This requires, of course, that such interpretations are acceptable for the reconstructivists. So first I'm going to illustrate what I mean here by looking at a quantum logical reconstruction of quantum mechanics. So could the quantum logical reconstructivist adopt representationalism by taking up the semantic rules of a psiontic interpretation? And I'm going to help myself of a paper that Guido Baciagalupi wrote in 2009. So the question here, whether, since the quantum logical reconstruction is based on deriving the Hilbert space formalism from orthomodular lattices, and I'm just going to ignore the several other assumptions that are needed for this derivation. The question is whether whether the orthomodular lattices are compatible with a psiontic interpretation. Now he argues that neither the de Broglie-Bohm interpretation nor the GRW or any other spontaneous collapse interpretation are compatible with quantum logic, that is, with a quantum logical reconstruction. In the first case, because the quantum kinematics requires classical logic. In the second case, because quantum dynamics requires classical logic. However, he argues also that the many worlds interpretation can admit of a change of logic. Nothing goes wrong if you drop the distributivity law, the classical distributivity law, and adopt instead a non-truth functional logic, like quantum logic. So it turns out that quantum mechanics reconstructed on the basis of quantum logic, reconstructed on the basis of orthomodular lattices, is compatible with a psiontic interpretation. So it seems possible to just take up the semantic rules of this psiontic interpretation, and so as a reconstructivist. However, in general, and I think this is something that is well known to all of you, reconstructivists have rejected psiontic interpretations. So I'm gonna look next at some arguments to this effect. There is one big and very nice argument by Jeff Bob, to the effect that psiontic interpretations are not rationally acceptable. But now the CBH reconstruction is not endorsed anymore. They have dropped it, mainly having to do with, failing the main purpose of reconstructions, that is making the standard formalism more intelligible, right? Deriving it from general, so abstract C-star algebras didn't do the job. But it's instructive to look at this because what actually justifies this conclusion is the premise that he has, premise number 7 here, which says if quantum theory doesn't break the empirical equivalence between quantum theory and psionic interpretations, then no psionic interpretation is rationally acceptable. So the conclusion is only good if this is accepted, right? So now he makes the case for hidden variable extensions, but he thinks this holds for many worlds interpretation as well. A similar argument, which I want to spend more time on, is provided by Hardy in the 2008 iteration of his initial paper on the reconstruction of quantum mechanics. Towards the end of the paper, he says something like this, referring to the 5 axioms that have been presented already in a previous talk. If we really believe these axioms to be reasonable, then they would also apply to hidden variables. And it would follow that the hidden variable substructure must look like quantum theory. We could not then use hidden variables to solve the measurement problem, since this relies on being able to give the hidden variables a classical probability interpretation. So what is the argument here? I'm going to go step by step, over all the premises that I think are needed for the argument to go through. First premise, if Hardy's axioms are reasonable, then they apply to any hidden variable extension, or as he later would put it, they are ontologically embedded in any hidden variable extension of quantum mechanics. It's not clear what that means, right? How would axioms apply to any extension, any interpretation of quantum mechanics? What does it mean to say that they are ontologically embedded? Right? There is a mix here of different languages, right? A syntactic language, there's a mix between syntax and semantics that is, troubling if you're used to making, the distinctions that need to be made. So let me go on. If these axioms apply to any hidden variable extensions, then any such extension must look like quantum mechanics, which I take it means that any such extension is or must be empirically equivalent or predictively equivalent to quantum mechanics. If that's so, if looking like quantum mechanics means that they are equivalent, then the extension or the psionic interpretation cannot solve the measurement problem. So that makes it unacceptable, unless one has alternative reasons for making it so. Okay? So this is a second argument that shows that psionic interpretations are actually to be rejected by the Reconstructivist. There is another more recent argument provided by Adam Koberinsky and Markus Müller in a paper that you've seen quoted over and over again at this conference. They say that psionic interpretations have a deficiency with respect to their explanatory power. Right? None of Bohmian mechanics, Everettian quantum theory, or collapse theories fill the explanatory role of a principal theory. Neither do they fill the explanatory role of a constructive theory. One thing to note here is this assumption that principal theories have explanatory power. This goes way beyond what Einstein intended in 1919 when he made the distinction, right? he said, well, it is constructive theories that have explanatory power, that provide understanding. Right? Principal theories, not so much. What they do provide is what he called logical perfection. Right? So you reconstruct a physical theory as a principal theory, not for the sake of increasing understanding of any natural phenomena, but for the sake of its logical, the theory's logical perfection, whatever that means. Okay, so here's the argument again for simplicity in premise-conclusion form. I take Marcus and Adam to say the following. A physical theory has the explanatory power of a principal theory only if it is reconstructed in the general framework from simple principles. It has the explanatory power of a constructive theory only if it increases the success of its predecessors. No psiontic interpretation has been so reconstructed, and no such interpretation has increased the success of quantum mechanics. Therefore, no psiontic interpretation has the explanatory power of a principal theory or a constructive theory. Therefore, they have to be rejected as explanatorily deficient or defective. So, if that's the case, if we take this at face value, then it looks like it's hardly acceptable for the reconstructivists to adopt any of the semantic rules of any of the psiontic interpretations. And this may very well be the case, the classical case of throwing the baby out with the water. Can it be avoided? Well, yes. Müller and Koberinsky suggest that the reconstructivists should adopt a psi-epistemic, or could adopt a psi-epistemic interpretation. But I want to explore the second answer here. No, this cannot be avoided. The reconstructivists should instead adopt inferentialism. And again, my interest is in whether inferentialism is compatible with reconstruction, right? Is there anything like this double epistemic benefit or not? So, I'm going to present an argument to the effect that inferentialism cannot, that if you're a reconstructivist, you cannot adopt an inferentialist metasemantics. That is, you cannot take on board the idea that what makes it the case that quantum mechanical expressions in reconstructed quantum mechanics have meaning is the inferential use of such expressions, right? So, again, the inferentialism maintains, Haley's inferentialism maintains that the meaning of all expressions is determined in virtue of their inferential use. Apply this to GPT reconstructions and to quantum mechanics, right? We have the two premises of the argument. The meaning of, such expressions as on the slide, state, property, probability, so on and so forth, in the language of GPTs is determined in virtue of their inferential use in general probabilistic theories. And the meaning of their counterpart, quantum mechanical counterparts, in the language of quantum mechanics is determined in virtue of their inferential use in quantum mechanics. But these are different theories, right? And so, presumably, at least. And so it follows that the meaning expressions in general probabilistic theories, state, property, probability, and so on and so forth, is different than that of their quantum mechanical counterparts. Just because the material inferences in general probabilistic theories are different than the material inferences in quantum mechanics. And so, general probabilistic theories, it follows quite simply, general probabilistic theoretical reconstructions of QM are not meaning preserving. And I suspect this is something that the reconstructivist would not like so much. Now there is a suggestion as to how to modify here the second premise, right? Instead of saying that quantum mechanical expressions like this, the meaning of them is determined in virtue of their inferential use in quantum mechanics, we may perhaps say that they are determined in virtue of the first principles of the reconstruction. So the first principles of a general probabilistic theory in particular. It's not clear what that means in the first place, but let's take into account. So if we modify the second premise to say that the meaning of quantum mechanical expressions are determined is determined in virtue of the general principles of general probabilistic theories, then that seems to require semantic rules, because then you have quantum mechanical expressions, the meaning of which is determined in virtue of what happens inferentially in general probabilistic theories. But you need semantic rules to carry on that meaning in quantum mechanics. And this is precisely what reconstructivists have provided. Semantic rules like this. Marcus Müller says a state, a quantum state, is an equivalence class of preparation procedures. Preparation procedures, this is an expression in the language of general probabilistic theories, right? So, I mean, this is something that reconstructivists have been doing no matter what the theory was that they wanted to reconstruct. Here is Bertrand Russell reconstructing mathematics, doing precisely the same thing, giving semantic rules, that is, or correspondence rules, that carry the meaning of natural number from the logical theory of classes, right, which is the basis for his logical reconstruction of mathematics. Now, even more problematically, if you take the meaning of quantum mechanical expressions to be determined in virtue of general principles of GPTs, then that makes the material inferences of quantum mechanics metasemantically idle. They don't do anything to explain or to determine the meaning of quantum mechanical expressions. But this goes precisely against what Healy maintains with respect to quantum mechanics. Remember, it is the material inferences in quantum mechanics, like those that I've illustrated above, that are responsible for determining the meaning of terms like quantum state, quantum property, probability, and so on and so forth. Right? So this is something that the inferentialist wouldn't I suspect, like at all. Okay, so to conclude, I've expressed interest in the question in virtue of what do expressions in the language of reconstructed quantum mechanics have meaning. I have then motivated the question about whether reconstructions can determine the meaning of quantum mechanical expressions inferentially, but I suggested that inferentialism is insufficient to explain what makes it the case that the expressions of reconstructed quantum mechanics have meaning. And if this is correct, then reconstructions of quantum mechanics, the whole program of reconstructing quantum mechanics, constitutes a serious objection to quantum inferentialism. Thank you. That's all.
Okay, thank you so much for this great talk.
Yes, thank you. I must admit that I didn't understand it because, well, I probably just don't know what semantic meaning is. But let me just turn this into a maybe provocative question. Let's say I'm somebody who just uses quantum mechanics, a formalism, for the purposes of inference. Just uses it very successfully. So why should I care about your objections? Because it works for me. I know what the terms mean. I know how to use the terms. At least I know in my informal meaning of mean what the terms mean. So why should I care that there is some sophisticated framework of logic and semantics and syntax where this somehow doesn't fit together?
Well, okay, thanks. I mean, obviously, the person you're describing is not Healy. Is not a quantum inferentialist. A quantum inferentialist would like to say that the meaning of quantum mechanics is determined inferentially. That is, if it has any meaning, that is. And I think it would be hard to admit that quantum mechanics is meaningless, right? So if you don't want to go that way, if you want to argue that there is some meaning that accrues to the linguistic expressions, the mathematics, the formalism of quantum mechanics, you have to have a story about it, right? I mean, you're free to use it the way you like it. If you don't care about whether it means anything, and if you don't care about explaining what makes it the case that it means what it does, then yeah, I mean, this doesn't speak to you. But then you leave something unexplained, right? Which some other people, among others, Haley himself, find it interesting, right? Does that answer what you had? I mean, you can take another way to answer the question is you can say, well, I know very well what quantum mechanics means. I know very well what meaning attaches to the expressions of quantum mechanics, right? But that's just a brute fact. It doesn't allow any explanation. It's just, the way it is, right? But I don't find it satisfactory. I mean, for the same reason that you look for an explanation of natural phenomena. You want to know, right, what explains the behavior of physical systems. Pretty much the same way you want to know what explains semantic facts, that is, facts related to what physicists mean by the language they're using.
Okay, we have a couple of follow-ups.
Maybe this is related to what Rudiger was wondering. Are you basically saying that this might be inadequate because the inferentialism concept is trying to claim that it gets its own meaning from the inference itself, so it's sort of a circular kind of justification? It's not circular? Or?
No, I don't think inferentialism is circular at all. I mean, there is... if the objections, and I have more objections against inferentialism that I presented here, but if they can be met, I think it is a very attractive view about the question about the meaning of quantum mechanics. Right. So it's not circular. The view according to which meaning is used is a very respectable position to have in philosophy, right? People like Wittgenstein and Brandom and Sellers have all advocated it.
Chris, is yours a follow-up to this?
So you seem to express a dissatisfaction with taking the semantics as a brute fact. Would you have a similar reaction, or at least most physicists, young physicists, when they learn Newton's laws and F equals ma. And in physics, it's usually presented as this is simply a brute fact. You can't go beyond this. Do you find a similar dissatisfaction with that? And if not, how is the issue of brute fact there different from the issue of brute fact here?
Yeah, that's a difficult question, right? The acceptability of brute facts, whatever kinds of facts you have in mind, right? Physical facts or semantic facts or moral facts, whatever they are, right? Is it acceptable to believe that they're brute? That is, that they don't allow any explanation? I don't know. But I think pursuing this explanatory, pursuing this line of thinking that looks for an explanation of such facts is interesting, right? So, I mean, it's fun. If you want to say, well, not so much, then I don't know. I have to disagree, but I don't have a strong reason against the existence of brute facts. There may very well be brute facts everywhere, right? In this case, this whole enterprise is just misguided, right?
Okay.
But then the burden is on your side. Defend the bruteness of facts. semantic facts in particular.
Okay. Rüdiger has a follow-up question.
Well, it's basically, you just segued, at least in my mind, from...
I have done what?
You segued from the question of semantic meaning to explanations. So could you explain how that works? Because because originally it wasn't clear to me that they were connected.
Right. So remember the distinction that I pointed out. I pointed to a distinction that Stolnaker makes between descriptive semantics and foundational semantics. Right? Maybe I can go back to that. So the point there is that whenever actually I don't need the code. Whenever we say that a certain expression, right, means something, right, that is a fact. It's a fact about the language that contains that expression, right? If it's a quantum mechanical expression, that is a fact, a semantic fact about the language of quantum mechanics, right? So an expression means something, right? That is a fact. The fact that it means what it does, right? It's not a physical fact, it's a semantic fact, right? And so the whole business of meta-semantics is to look for explanations of those facts. In virtue of what do semantic facts hold, right? Like, after all, I might actually... Oops. Right, here's how he put it. What makes it the case that a certain language has a particular semantic? So you might put the same point in terms of grounds. What is it that grounds those semantic facts? That is, facts according to which a certain expression means something. Right? What is the ground for that association between linguistic entities and non-linguistic entities, right?
Okay, thank you for your informative talk. I have a question, or well, maybe an observation. At some point you said that GPTs are sort of not meaning conserving, in the sense that...
Meaning preserving, yes.
Preserving, yeah. So if I do something within a GPT and I use words like state and property, etc., then I might draw some conclusions from that, but it doesn't help me in drawing similar conclusions about when I do the similar thing in quantum mechanics. I think there's an interesting structural analogy here to, I think, a problem which is known in physics. If I measure lengths, I have different procedures to do that. So I can think of ordinary length using a meter, but then if I go to astronomical distances, I'm not using a meter, I'm using a different procedure to do that. And I think it's a bit of hard work to actually say that these two concepts which I introduced for lengths via my measurement procedures are actually referring to the same thing. And I was wondering whether this sort of analogy could possibly help to bridge that, that problem which you have pointed out here.
I have no idea if it can. I mean, I don't really see the analogy. So the analogy between having different measuring procedures and having different theories with different inferential rules and different sets of material inferences that determine the meaning of the distinct vocabularies.
It's not the same thing.
Yeah.
I thought maybe it might help
Yeah.
to think about it.
I should think about it, yes. Thank you.
Thank you for the nice talk. I'm wondering if Frege's contextuality, for meaning or semantics has anything to do with this discussion. And so that's one question. And then you also mentioned the possibility of conflating meaning and ontology, which the interpretations do. So do you think that...
Some of them at least.
Yeah. So do you think if we pick that option, we can avoid some of these issues?
The option being Frege's...
No. Conflating meaning and ontology. So there are two different questions. There's one question about contextuality of semantics, and then there's a question of taking the ontology to be the semantics.
Right. Good. So first question. Yes, actually, Frege's principle is relevant to the whole, the general inferentialist view on semantics for natural language, because the unit of meaning for both Frege and the inferentialist is the judgment, right? The sentence in a language, right? So that, because it's sentences that we're using to make inferences, right? And that raises the question about, well, how is it that substantial expressions like, singular terms acquire their meaning inferentially, right? So this is a well-known problem for inferentialism. Several people have addressed this. This is one of the problems that Healy inherits from the general inferentialist view put forth by people like Sellers and Brandom. He never seemed to care about these inherited problems, but I think that is a mistake. So you're right to point out to this principle endorsed by Frege, justified by Frege. Second question, if you conflate semantics and ontology, and you take then the semantic rules to specify the meaning of quantum mechanical expressions by identifying bits of physical reality, right? Then you're just, endorsing the semantic rules of a psiontic interpretation, right?
Yeah. Isn't that reasonable?
I'm sorry?
Isn't that reasonable?
It's very reasonable. I don't see... there are problems with that, of course, but that's not what I've been, criticizing here, right? I've looked at the alternative. The alternative being that, there is this other metasemantic view, non-representationalism or inferentialism, that might also be considered as an option for the reconstructivist, right? And as you've seen, reconstructivists seem to generally reject psiontic interpretations, thereby rejecting semantic rules as a way of, specifying the meaning of quantum mechanical expressions.
Thank you.
Yeah.
Thank you. Very interesting. So I'm wondering with this slide as well, what if we consider QM to be like a special case in this GPT? Does that change this this slide here?
Well, even if it's a special case, it's still a different theory, right? It has material inferences of its own. It has presumably inferential rules of its own. So that seems to be enough to justify this point that counterpart expressions, the quantum mechanical counterparts of GPT's expressions have a different meaning. If we take, the inferentialist story for granted, that is, if we take the meaning of expressions to be, determined by material inferences, right?
Is it possible to have mappings between that are going to be meaning preserving?
That's a very good question. That would be very interesting to look into. If you can have at least if you can have at least a small class of mappings that are actually meaning preserving. Yeah, that would be a way of going against this argument, which is, I think, better than the way suggested by Greenbaum's rather naive understanding of semantics.
Thanks.
Mm-hmm.
Okay, and then we have a final question by Mike. Sorry? Was this okay? Okay, so then let's thank again Iulian for the great talk.
Thank you.